everyone, and thank you for coming to our talk. This talk is for you if you're interested in running really generative AI models on your own infrastructure in a secure way. Across the number of companies we're talking to, we're seeing that lots of businesses are becoming more wary of putting their data on proprietary hosted AI platforms. And what we're going to do today is show you an alternative solution where you can host your own LLMs on your own infrastructure. And every time you blink and you realize the AI landscape has changed quite a bit. And we're seeing also that lots of people look at this as, this is quite complex. And what we're trying to do today is peel back that complexity and start this, this journey from very, very basic building blocks and take you through how sort of our experiences building AI platforms out of Kubernetes and open source LLMs. We want to talk about patterns that we've used, pitfalls that we stumbled into, and really talk about our mistakes as well, so you don't have to do them yourselves. And we'll also talk about the layers that we build on top of a basic open LLM running on Kubernetes. Before we move on, I'm going to take a moment to introduce ourselves. So, my name is Priya. I'm a technology architect. I've worked in many small and large businesses, and most of my background is in DevOps as well as consulting. And my current environment I work in is around building identity and access layer on top of GenAI applications. And over the number of years I've worked on building machine learning pipelines as well as automating these pipelines. And so this is quite an exciting area to be working in. Over to Luke for an introduction.
Cool. Hi, everyone. Yeah, I'm Luke Marsden. I've worked in DevOps pretty much my whole career. I started out doing a startup that did storage for Docker and Kubernetes back in the early Docker and Kubernetes days. I was involved in SIG cluster lifecycle at the time that we created kubeadm. So if anyone's used kubeadm here, you can blame me. And then I've done, like a string of startups. So we then did an end-to-end MLOps platform before AI was cool. And then I did consulting for a few years while during the time that the ChatGPT moment happened. And so I saw firsthand working with those clients the opportunity to take open source models that were getting better really quickly and run them locally in Kubernetes clusters for improved kind of security and reliability. So yeah, it's an interesting topic and happy to share some of our learnings today.
Cool. We're going to start really, really basic. So what is an LLM? So if you're sitting in this room and this is new language for you, probably isn't, but then I'm going to introduce it really quickly just to lay enough context to go on to the nuances of running these on Kubernetes. So the mathematical explanation, very simplified, of an LLM is that it's a multi-dimensional function that maps sentences onto other sentences. And the input is a phrase, for example, what is the capital of France? So that gets turned into a vector. That's basically a string of numbers. And then you're reading the values of this high-dimensional coordinates, getting the answer, turning that back into a sentence, and returning it back to the user. This is much more easier when you've got a GPU. And I guess why run LLMs on Kubernetes and what do you need? The very basic thing you need is access to a GPU processor, a TPU or GPU. And you could get that as a hardware, basically go and buy off a GPU, run it in your office like Luke does, has the added advantage of warming up your office in winter. But then you could also might as well get it off any one of these cloud providers, so across Google or AWS and or Cilium. That's just not enough. So let's say you want to do something with that. You would need to connect your GPU cluster to your Kubernetes cluster. And that's done with a device plugin that makes your GPU accessible into your Kubernetes cluster. But sort of like, let's step back. Why bother? Why go through all this trouble so you can run these LLMs locally on your cluster? So the main driver we're seeing is security and compliance. So lots of customers we speak to who are either in a healthcare business, or if you're a European telco, where you store your data is quite critical. And this is not just data residency, but also where your data gets processed. So which means a lot of the hosted LLM platforms are completely out of scope. And then going on, availability and latency is a big deal as well. The closer your LLM is to you, more likely that you'll get your answers back quicker. So that's, and we're also seeing that hosted AI platforms like the ones around today, uptime and API response is still quite shaky at the moment. So you're in control of your infrastructure. We're also, we live in an interesting era where it looks like open source LLMs, it looks like they may be overtaking a lot of the proprietary stuff. And I'm sure most of you have heard of DeepSeek at this time. And the last driver that I'm going to talk about is the cost of ownership. The longer you run these and the more at scale you're running these LLMs, the cost starts shifting. So if it's a quick POC, then great, you get an OpenAI token and you're running. But then if it's something where you want your model to think longer, so a lot of these LLMs that pretty much like DeepSeek, they are LLMs that are sort of like a chain of thought model. So the longer they think, the better answers you get. And this is where the cost starts shifting quite a big deal into your locally hosted LLMs. By local, I don't really mean on your laptop, but I mean any kind of environment that is accessible to you on the cloud or on a server farm. It doesn't matter. It's still local. Cool. And lastly, I'm just going to quickly say why Kubernetes. It's really just because Kubernetes is Kubernetes, because of portability, because of consistency, and scalability. And it's just that you can apply the exact same pod spec on your server farm, or you can apply it locally, and you've got that consistent environment accessible. Cool. This talk, as I said, is a series of demos, and on every slide you can see a QR code to a GitHub repository. So this repository has got a README file with all of the instructions in terms of commands we're going to show you today, as well as a walkthrough of what else you could do on your Kubernetes cluster. Our first demo is going to pull in a very simple open source product called Ollama, and this is predominantly used to test out LLMs, and we're going to use a Helm chart to pull in Ollama along with Open Web UI. Over to Luke.
Yeah, cool. So I'm just checking these mics work. Okay, great. So here we've got a Kubernetes cluster with a single A100 in it, and what we can see is that we've got Open Web UI and Ollama running in that cluster. And then if we go into Open Web UI, I'm going to start by showing you kind of one of the challenges that you get with this setup when you get it kind of out of the box. And so what I'm going to show here is a prompt that we wanted to have work when doing an API integration between an LLM and an external system, like in this case Jira. So the prompt is to try and present the key information from an API response body, including the user's question. So we get the user's question, which is what issues are there, and then we get the API response, which comes back from Jira. And as you can see, even though this is just a sprint with 10 issues in it, the API response body is quite big. And so this highlights one of the issues that you get with Ollama out of the box, which is that it has a truncated context length window. And so what you can see specifically here is that even though we gave the LLM which should be capable of doing a good job on this task, where the task is summarize the issues in the sprint, what it actually came back with was a bad answer. And in particular, it started talking about the JSON response body, it talked about the root element, and in particular, it said the root element is an array containing one object. But it's not. The response body had 10 objects in it. It had 10 issues in the sprint. And so I'm going to pass back to Priya to explain why that happened, and then we're going to talk about how we can solve it.
Cool, thank you. So the model that you're running by default when you're using Ollama is a highly compressed model. So what it means is that it's a quantized model. And these are really meant to run on test environments like your laptop. And it's not really tuned for a production environment. And especially the one that Luke just demoed, that's a model that's compressed to store 4 bits of information per weight in the neural network. And this is pretty, it's sort of, I wouldn't say it's very low resolution, but it's low enough that sometimes your answers will come back garbled, sometimes it will just say some random stuff. And we've seen that pushing that quantization to 8 bits, it sort of gives you that sweet spot between something that's practical and something that's performant enough. So that's your Ollama's quantization trade-offs there. And we've also seen that some really important environment variables are turned off by default. So one such variable is called flash attention. And flash attention is, I think, turning it on reduces the amount of memory you use when your LLMs are answering questions. It effectively reduces the memory needed to return back an answer. And we've seen that turning on flash attention takes that response memory usage from quadratic to subquadratic with context length. So why did Ollama break context length? Why did they give us a very highly quantized model? Why did they turn off variables, flash attention and other variables? The reason being that it's meant to run on your, say, MacBook, where you're competing for memory with Chrome and Slack and all your other enterprise software. So it's not something, you can take it to production with a lot of tweaks, but then you quickly move on from using Ollama to another very popular project called vLLM. And vLLM is an inference engine, an inference server, and it's effectively the base on which we serve our models. So over to Luke to give you a demo of that.
Cool, so let me just find that, sorry. Okay, so yeah, here we have, right, sorry, just found the right part of the video. So here we have another Kubernetes cluster. This one has 2 A100s in it because it's running a few different models, which we'll look at later. But in particular, let's focus on this vLLM instance here, which is running Phi 4 from Microsoft. So what we've done is we've run the Helix stack on top of this vLLM instance. And what you can see is that when we said hi to Phi 4, it responded very, very quickly. And so, as Priya was saying, vLLM did a really good job of optimizing the latency on responses and the number of tokens per second. And you end up with a system which is very performant. And it also comes with better context length defaults. So it's kind of closer to something you'd want to run in production. So what I'm now going to show you is applying an AI spec, which I'll explain what that is later. But the AI spec corresponds to this app, which is for Jira issues in this case. And what I can show you here is that now that we've got vLLM running with a proper context length set up, it does a much better job of answering this question to summarize all of the issues in the sprint. And it actually gives you 10 issues back rather than, as Ollama did, truncating the response. So yeah, that's vLLM. Very good project, recommend it.
Yeah, cool. On this Kubernetes spec on sort of the right side here.
Sorry.
You can see a few things here. One is that we're pulling in Mistral 7B, and alongside the fact that we're using vLLM. One of the gotchas here is that vLLM downloads all the weights that are needed for this model from huggingface.com. So and getting those weights is a gated process, involves, of course, signing terms and conditions, but also it means you're constrained in the sense that your cluster needs to have access to the internet. And the whole idea of running things privately is so that you can have things in your air-gapped environment. So in order to do that, we kind of scratched our heads and we wondered, how can we, do we need to invest in a model registry? And then we said, no, we don't. Let's just use our Docker registry. And so we baked the weights of the model into the Docker image along with the model, and we checked that into Docker registry. We did run into a few issues here, though. One being that Docker by default uses a gzip level 8 compression model, and this means that it just takes quite some time for the model to get up and running and answer questions. So we then had to patch the machine building the Docker images to use a custom compression algorithm. And pretty much everything else runs as normal. But then that's sort of where we got to. Let's again step back a bit. What are we doing here? We're serving Mistral 7B, but then there are very many models that do very different things really well. There are image models, there are multilingual models, and in this mechanism, you're sort of at this point where you need a completely separate node pool for different types of models. And that's sort of where your costs become limiting. So we then decided we've got to find a way to run multiple models, but also have GPU memory sharing in place. And that's sort of where we said, we're all good cloud engineers, let's build our own scheduler. So that is one thing. But then the other thing is you're increasing your memory utilization on your cluster. You've got a production ready-ish environment where you can serve multiple models. You can also mix fine-tuning along with inference jobs, which then means you've got a wider set of tasks you can do with your models. This is all great, but then what's really valuable to the end user is what you build on top. Why are we serving these models? So Luke's going to give us a run-through of that.
Cool, thank you, Priya. Yeah, so I want to talk a bit about the different layers on top and what you might want to build kind of on top of an LLM now that you've got it deployed. So now that you've got an LLM and you've got like a chat interface to it, well, what are you going to do with it? Well, you could ask it to count the number of R's in strawberry, and maybe it will. You can ask it to tell you a joke, but neither of those things are particularly useful in a business context. And in order to really get value out of an LLM that you're running in a Kubernetes cluster, you need to start connecting it to your business data and your business applications. And so those are two different types of integrations that I'll go into in a little bit more detail now about how you can do knowledge, which is also known as RAG, and API integrations. And then the other question is, like, how do you ensure the quality of the LLM product that you're shipping, like the LLM system? It's not just an LLM, it's all of the stuff around it. And the way that you do that is the same way that you do it with software and DevOps, which is that you write tests. But writing tests is a little bit different in this world of LLM applications. It's known as evals, which means evaluations. So what we did was we set up, we built a little CLI tool that uses an LLM as a judge to judge the output of the system and to then give you a pass or fail grade that you can then use in a CI/CD system in order to test the system. And we feel like this is super important because if you can apply the sort of same CI/CD process you use for the rest of your software to GenAI applications that are defined as configuration, like a CRD, then you can apply all of the existing kind of best practices and process that you have for your engineering teams to build and iterate on these things. So The next piece I want to share is like how the integrations work. So you actually saw a glimpse of the integrations in the demo I just did a second ago, where we made an API call into Jira as an example. And so let me explain, kind of break down for you like how that worked, because that's actually a multi-step process. So the first step is that, and each step in this process, by the way, is a prompt template. So it's like a prompt that can kind of get filled in. So the first prompt template is classifier. So it classifies whether the request needs an API call or not. Because if the model is just answering what is the capital of France, it doesn't need to make an API call to Jira to answer that question. But if you're asking how many issues are there in the sprint, or what's the current exchange rate, then the system is going to need to make an API call to an external system. So the first step is to just classify yes or no, and if yes, then which of the available tools. And then if the answer to the classifier was yes, then the next step is to actually ask the LLM to construct an API request body based on the user's query and the open API spec for that API. And amazingly, LLMs can do this. They can take an open API spec, they can take the user's question, and they can have a go at making at constructing an API call that can then be executed. So then the API response, so then the system that we built will make the API request and take the API response and then put that into the third template, which then summarizes the response back to the user. So that's API integrations. And the other major pattern, so API integrations, by the way, that was kind of like live queries against running systems. The other pattern is called knowledge, also known as retrieval augmented generation, although I think that RAG is an overly complicated term, and I prefer the word knowledge. The idea with knowledge is just to bring appropriate context, much like API calls, bring appropriate context to the LLM when it is doing inference. So this also happens in 3 steps. The first step is that you need a vector database. So a vector database, and there's good Postgres extensions for this now, by the way. We use pgvector and vectorcord. I recommend vectorcord, actually. We use it in production with a customer, even though it's quite an early project. It works very well, and it scales well. And so what you do with a vector database is you take your source documents and you chunk them up into pieces, and then you put each piece into the vector database, which then kind of maps the text in that document into a vector space, which then allows you to do a similarity search with the user's query. It's a very long way of saying that if the user asks a question, it will find relevant documents in the database and include those documents along with the user's question when sending that to the LLM. And that's the step 2, which is you take the prompt and the response, you pass it into the model, and then the model is kind of grounded in facts. And then the third step is that you can just regularly refresh that knowledge kind of as it changes. And then the last piece, oh, actually, no, I'll jump to the demo, sorry. So we pass that back to you. So there's a third demo here of knowledge. And I actually couldn't help myself. I had to share a demo of something that we just got working yesterday. So this is knowledge, but it's a kind of advanced knowledge pipeline that's called Vision RAG. And Phil's in the audience over there. He got this working like yesterday morning. So thank you, Phil. What we're going to see here, and actually just before I jump into that, let me explain how a Vision RAG pipeline works. So here we talked about putting text into the vector database and getting text back. Another thing you can do is you can use what's called a multimodal embedding model that can embed images and text into the same vector space. And then you can get images out of the vector database and then include them along with the user's question as images, and then feed that into the LLM, into a vision language model, like one that's able to understand images. So let me show you why that's a good idea. So here we have a text-only RAG pipeline. And the RAG pipeline has a PDF in it. And if we look here, we can look inside the PDF. So I think if we take this, so this is a financial paper, for example, about stock sentiment. And you can see that the paper has text in it that you can highlight, but it also has these tables. And it looks like the person who made this document took screenshots of Excel and pasted them into a Word document, pasted the screenshots. Because those images, those tables are images. So the problem is if you just take the text out of the PDF and put it through this existing kind of text RAG pipeline, we're asking a question here about this table in particular, the price change correlation table. And if we look at the result from the system is a fairly good summary of kind of the relevant topic, but it admits the exact 10-day sentiment lag for the energy sector isn't provided in the context, even though it was right there in the document. As a human, you can look at the document and you can see that. But because it was an image in the document, it wasn't able to do it. So we've added this new vision toggle in the system, and now this puts it through an image pipeline, like I just described, and it immediately gives you an answer. So it says the sentiment lag for the energy sector is 0.35. So if we go and look here, we can check, did it get the right answer? The energy sector, yes, it worked. So it's able to pull the exact right answer out of this document, even though it's like a complex document layout. So this is really basically an amazing information processing system. You've probably got loads of knowledge locked up in your organization, and you can use this approach to extract it reliably and make people more productive. So yeah, I'll take the mic. Thanks. So the last thing I want to mention is that we're working on this effort called the AI spec. And the AI spec, as you can see here, is an effort to define a new CRD type in Kubernetes that allows you to describe all of the applications that I've just shown you as configuration rather than code, because that allows you to avoid having GenAI sprawl in your across your company, where different teams might be building completely separate implementations of RAG pipelines, and then you need to figure out how to secure them all. If you instead define everything in terms of this configuration, then everyone can be iterating on the same type of thing, and you can use testing, the evals that I described, and CI/CD to result in less effort and better results. So that's all we've got. Thank you for coming to the talk. If you're interested in any of the things that we talked about today, then please connect with both of us on LinkedIn. In particular, if you're looking at building a GenAI developer platform of your own, and you are interested in collaborating on the AI spec, then please reach out to me. If you're working on these kinds of things and you'd like some help, then please also reach out to me. We're happy to talk to everyone and compare notes. So thank you very much.